Good afternoon, everyone. It's our pleasure to have another webinar sponsored this time by WTS FAU chapter that the President Valentina from Urban Planning is going to take care of the question and questions after the Aline's presentation. Please send your questions to the chat. Or you can pick up the microphone when the presentation is done and you can ask directly to the speaker. Today, we have Aline. It's my utmost pleasure to introduce Miss Aline Machado, a former student from our program that she just graduated with a master's degree in transportation at Florida Atlantic University, focusing on artificial intelligence, machine learning, simulation operations, and so on. During her studies, she conducted research at our center, the Freight Mobility Research Institute, in various areas, just freight transportation and ITS, Intelligent Transportation Systems. She have applied programming and data science to improve the overall transportation network performance. Usually, case studies goes from the Florida transportation network. And as a graduate student, she's also had leading positions at the WTS FAQ chapter and IT FAQ chapter. Also, she was assistant research coordinator for the center and was taking care all the IT involvement for the FMRI. Aline, the floor is yours, and thank you for this opportunity.
Thank you for this opportunity to present about this research. And this is actually FMRI Year 3 research project on identifying critical freight corridors. We use Florida as a case study, and we use decision support systems. And it was proposed by different stakeholders from FDOT. And if you have any questions, please address them in the end. This is the outline of this presentation, the introduction, problem being addressed, the objectives, a brief literature review, the methodology, a case study in the state of Florida, some conclusions, and some future research. So it is well known that the efficiency of freight transportation plays a strong influence in the local, regional, and national economy. And moving freight using trucks requires a high-quality transportation infrastructure of roads and highways. There are many challenges by the mere presence of heavy vehicles. For example, trucks require wider turning angles and operate at slower speeds, and heavy vehicles tend to degrade the transportation infrastructure more when compared to lighter automobiles. Traffic congestion impacts negatively in the efficiency of freight movements. Financial resources are limited, so choosing the best locations to advance infrastructure projects is important. In this sense, the FAST Act is a law from 2015 that established a series of programs to support and advance critical transportation projects, including freight-focused initiatives. And inside the National Highway Freight Network, there are critical urban and rural freight corridors, referred as UFC and CRFC. Critical freight corridors must have improved system performance and provide efficient access to freight-intensive facilities. These corridors are designated by state DOTs and MPOs in their statewide freight planning. In Florida, these corridors were defined in the Freight Mobility and Trade Plan of 2020, as seen in the map on the right. The FAST Act defines a series of criteria to designate these corridors, but overall, these criteria are flexible. And just as a small summary, the urban and rural classification is based on the population of the area. This is the overall process of designating critical freight corridors inside statewide freight plans. This is a recursive process because corridors can be redesignated as needed. One limitation is the maximum mileage for the state. For example, Florida has a limit of 320 miles for rural corridors and 160 miles for urban corridors. However, stakeholders cannot fund all projects and they must choose the best alternatives. To advance different projects in freight transportation, we need systematic decisions and planning methods. One approach, which is the one that we applied in this research, is to use a decision support system. Since assigning these corridors has several criteria to be considered and there are many corridor options within the transportation network, this can be defined as a type of multi-criteria decision-making, and more specifically, we apply the analytic hierarchy process, or AHP, which structure complex problems with multiple criteria in a simple hierarchy. Also, we use a GIS-based approach, making this methodology a multi-criteria spatial decision support system using AHP. And overall, the lack of a specific methodology for identifying critical freight corridors, both urban and rural, is the motivation of this research. And a solution should consider policy criteria, limitations, and input data variable. There was also observed a lack of integration in decision making and which criteria to prioritize depending on the state's needs, expertise, and future plans. The objective was to develop a framework to make the selection of these corridors a more transparent method, and this would support decisions and facilitate the corridor selection process. One final consideration is that since it's a programmatic approach, it can also be easily adjusted to other states and future freight funding policies with a similar structure. I'll briefly cover the literature review, starting with the FAST Act providing the criteria for developing this framework, and statewide freight plans and their methodology for designating critical freight corridors were analyzed for the states that they provide this type of methodology. For research about critical freight corridor investments, there was not found many sources. Some examples, like the two in the slide, one from 2014 and the other from 2019. In the area of decision support systems, we first analyzed the analytical hierarchy process, which is a form of decision support system and multi-criteria decision making, firstly introduced by Saati in 1987. This ranks decisions using comparisons between pairs in a matrix, and it is a method for weighting scores to derive an important scale of items and criteria in relation to each other. There are several examples of application of AHP in transportation, such as the ones listed in the slide. And we also included research that integrates GIS in decision support systems, such as the one listed. I will not get into much detail. For our methodology, we developed a ranking system for highway corridors based on the criteria selected as important by the decision maker. And the criteria that defines the eligibility of each corridor is defined by the FAST Act. The steps of data collection, organization, fusion, and compatibility aggregates all data as a graph representing the transportation links and nodes. And after developing the decision support system, we develop different scenarios and choose corridors from high scoring links. And I'm going to detail the step of defining the decision support system. This is a problem hierarchy for the AHP solution, the goal criteria, and the alternatives. Criteria A to G pertains to rural corridors, and I'm going to detail them in the following slides. And criteria H to K pertains to urban corridors. And the solution alternatives are the different corridors combination based on which area they're in, urban or rural. These are the criteria provided by the FHWA in the FAST Act, and rural corridors can be designed based on truck ADT, access to energy-related areas, connecting different freight facilities, etc. Urban corridors should provide connection to intermodal freight facilities, alternate routes, major freight generators, And we should note the last criteria for both corridors, which is the one that gives the most flexibility to designate free corridors. Given those criteria, the model formulation applies different weights for the analysis. For rural corridors, this is the evaluation equation, and S is the final score calculated for the rural corridor. C is a decision variable that said the criteria was met, W is the weight, R is the index from 1 to 7 related to criteria from A to G, and corridors with higher score will be selected as eligible. This is the evaluation for urban corridors, which is pretty similar to the previous one. The only difference is that the index is from 8 to 11, and the same decision values for the score is applicable. Over 0 is eligible, and equal to 0 is not eligible. The weighting method used is the one proposed by Saati, and we can use only the main scale of importance, which is enough for this one. The stakeholder is free to use intermediate values as needed. To determine if the corridors are eligible or not, we should have certain data according to each criteria description. Starting with census definition of rural and urban areas for corridors inside rural areas, criteria A, eligibility will be based on the functional classification and truck ADT, criteria B based on energy exploration, and etc. until criteria F. Oops. Sorry. And for corridors inside urban areas, criteria E related to intermodal facilities, parallel routes, criteria J requires the location of rate-intensive industry facilities, criteria K is the broad range, so some of them, they're common to both areas as we noted, and we aggregated the data sources, and after defining the criteria according to the type of corridor, we evaluate link information and generate the final rank. Implementing an automated method for critical corridor allows a faster and more accurate designation and redesignation. And this can be developed in any programming language. For the case study, we used ArcGIS and Python. When we have our network ready, we should start applying the rules, and I will now show the process of each type of corridor. This is the overall framework for setting the values of the criteria, which is the on and off variable based on the data inputted on both links and point information. Therefore, it's simply the backward process of each data is required for each criterion. This is the final framework for calculating the corridor score. It consists of iterations of each corridor in the database, a different method for corridors in each category, rural and urban. And when all corridors have its own score, the results can be presented in maps with the score range. For testing the method, we applied the development methodology in the state of Florida, which already has a network of critical freight corridors, which was updated in the year of 2020. An integration of all the listed data was performed in a unified database. And according to the steps presenting, so this is just a sample of the data that was gathered. And the steps presenting the previous slide this is an overall overlook of the task performing in the GIS software and in the Python. Using this methodology, different critical freight corridors can be obtained based on a different combination of weight attributes. So with the help of stakeholders, we generated different scenarios. So the first one is a network of critical corridors considering all criteria equally. We then create different focuses, such as benefiting freight-intensive facilities. For this, we attribute a scale of 5, which is an essential or strong importance. And for freight-intensive facilities, criteria C and H have a higher importance, for example. The same was done for intermodal facilities, international ports of entry, intensive use corridors by volume, energy exploration. And finally, we tried to generate the corridor floors for validation purposes. This is just a sample of the HP process of pairwise comparison, and this should be the matrix of giving a benefit to freight-intensive facilities in the urban category, for example. The rows correspond to the criteria being prioritized, and the columns correspond to the criteria being compared. And we then transform the pairwise comparison to a standardized matrix, which are the weights. The scenario of equal weighted criteria shows all options of eligible that are eligible for critical freight corridor designation. So for Florida, using the range of scores, this was the map result. And in the case of a large state such as Florida, many sections of highways can be eligible. So this first scenario would not narrow down the options, and we should choose one or more criteria for a more effective decision support system. So, or the second result that we present is giving a benefit to freight-intensive facilities, which also generate a relatively large selection of links, but with a more defined look, as seen in the map. And we also noticed that applying the scenario would be more useful for the rural corridor category. For corridors based on sections of road with high truck traffic, this was the results for Florida, another example of the results generated. And in urban areas, there are significant freight activity, so there is a large selection of corridors. And for rural areas, there are less freight traffic, but still some corridors are eligible. So since less corridors were selected, this scenario is also suitable for application in this category, which narrows down options, which is what we wanted with this decision support system. And we also ran the algorithm and calibrated to reflect Florida policies, which projects it wanted to develop in the state, and these were the corridors generated. This network was highly similar to the current Florida critical urban and rural freight corridors after calibration, with some differences in the highlighted areas. So you may ask, why should we use this approach? It allows easier redesignation due to automation and the ability to evaluate different options, which is not exactly possible without a systematic approach. Maybe the previously presented perspectives would have led to a different designation in the most recent freight plan, for example. But in the end, it is always the stakeholder decision, and the developed framework is just a support. That is why it's called a decision support system. Some considerations to this project is that this is a rigid solution to a highly flexible process. So it is necessary to add more variables to allow more flexibility. Another limitation is related to data, which would require private sector inputs. And more validation of the method is ongoing, involving several stakeholders, maybe applying in other states, for example. This is a brief summary of this presentation. I tried to keep it as short as possible. And future research could test different weights and evaluate past corridor designation. Also incorporate first and last mile factor as recommended by FHWA. And the possibilities are endless for expanding this work. So thank you all, and if you have any questions, I'll take them, or feel free to email me.
Thank you, Aline. At this time, if anyone has any questions, feel free to speak up or put them on the chat.
Aline, thank you for your presentation. I have two questions. The first question is, during your research, what is the most challenging issue for you?
I would say the biggest challenge was that in the beginning, I did the backwards process. So first, I tried to build a methodology to select those corridors, try to automate as much as possible. And then I tried to find different maybe methodologies or theories that were already existing that would base why I chose this methodology. So I would say this was the biggest challenge. Another one was finding data information to input in this model, because this is a data intensive application. So basically, the more data you have, the more variety you can generate for results. The less data you have, the more limited, and maybe it wouldn't be as suitable. So I would say those would be the main challenges of this work.
Thank you. And also, we are familiar with other type of work or research that has been done in the different states. How your work is different from the work that has been done, let's say in Texas or in Maryland, and continue on this is, can we apply your methodology in the different states?
Yes, this can be applied in different states, given that the state would suit to its needs. So you could, for example, if a state doesn't want to focus on freight intensive facilities and instead it wants to focus on only highway sections of highways which has a high truck ADT, for example, it can match the methodologies to suit its needs in terms of knowledge and data available, and also the future plans that it has for the state, what types of areas they want to expand. And your first question was what it differs from different ones. I would say it applies the AHP. I couldn't find any work that would relate critical freight corridors and AHP. Also, decision support system, most of them, they use only a GIS approach and empiric methods. So this creates a more automatic decision. And also, if a state implements this method, then redesignation, it's easier. And since it is a GIS approach, which not all states they apply that, being approved for the critical corridors, it's an easier process for the Federal Highway Administration. So since this is a GIS approach, it benefits from this part, just to speed up the process.
Thank you, Aline. We have some questions, Valentina. We have some questions on the chat.
Yes, so we have a question from Pepper. Would the infrastructure bill in Congress make any changes to the designation process for CUFCs and CRFCs?
So with the new changes for the designation process, if there are any changes, this method allows, for example, if there are new criteria or if there were some criteria suppressed, I would say the only thing that it would be necessary, it would be to tailor the equation to eliminate the ones that are not included and then add the ones that are included. That is why it's a flexible model.
Thank you, Aline. We have another question from Pepper. What exactly are the data sources needed from the private sector?
This was something that we were looking in the beginning to try to build a very comprehensive data sets. So I would say the more data you have, the better you can apply. And this is true for any data hungry application such as this one. So for example, if we have historical data showing that a certain part of a state shows a potential for development, then this is something that the state could look into and use as a critical corridor designation, use that part for a critical corridor designation. So I would say historical data, more detailed data, Also, for example, warehouses, they're changing all the time. Ports and airports, they're more fixed, but private sector locations of trade-intensive facilities, for example, they change all the time. So having this input would be extremely beneficial, like I mentioned, for the first and last mile factor, and this would be a future research. So this would be something that could be solved with private sector data.
Another question. The FAST Act provided the states a limited number of miles to designate as critical urban or rural corridors. With the decision support model you have created there, were clear discontinuous segments within the results. Do you think that more mileage would be beneficial in creating a connected network?
The more mileage could benefit from creating a more connected network, but also the decisions, like I mentioned, the system can show results even in all the corridors that are eligible or just the top. So yes, the top choices would be a very disconnected network. So actually it would need a second input from the stakeholder. So it would need to decide, do I want this disconnected network? Mostly you won't want it. So for example, you can try to pick from choices that are, for example, not in the top, not in the top beginning of the malleage, but you can, it's kind of like making a puzzle. So adding some sessions that are not uh, as with a high score, but to benefit a section that had a really high score according to the criteria that was decided, it could be more beneficial than creating a disconnected network. I don't know if it answers, but it always needs an extra step, which is what is the final decision from the stakeholder of which corridors to apply.
Did this work incorporate scenario planning for future planning?
It can incorporate, but in a more indirect form. So this, for example, if another study is conducted with future scenarios, the results of this study could be incorporated in as an input for this methodology. So one thing that this is not it's an analysis of future scenarios. So it takes inputs from other studies, such as analyzing future scenarios, but it doesn't exactly does that. So this will be kind of like another project that would be incorporated in this one.
Isn't it okay for the CUFCs and CRFCs to be discontinuous because they're meant to connect to other elements of a state's freight road network, for example, interstates?
Yeah, this is also something that I mentioned in the one of the limitations is that maybe we could add another um, maybe another weighting method or another variable. So adding more variables that would say, I would rather create a more connected network. This is possible. So this would be, for example, a chance for future research. Adding new variables to account for a more connected network, for example. Do they have any other questions?
It looks like those are all of the questions that we have. Thank you, Aline. Thank you for addressing all of the questions. If anyone has any other questions, please put them in the chat. We'll wait maybe like 5 more minutes for any other questions.
Yeah, we're good if we don't have any more questions to end it earlier. I tried to summarize it as much as possible. Maybe I summarized it too much. but I hope it was comprehensive. And by the way, this is in this we should have the final report published in the FMRI website anytime soon. So if you want to see the final report for this research, you can find it in the FMRI website in the future.
Thank you, Aline. Thank you, everyone, for attending. I do want to let everyone know that we will be having another webinar in September 29th in partnership with ITE. Dr. Dimitris will be the presenter, and he'll be presenting business ecosystem in supply chain changes and prospects. You should all be receiving an email regarding that webinar soon.
All right, thank you for the opportunity of presenting today. Thank you, Valentina,
Thank you, Aline. Thank you.
and thank you, Dr. Kaiser.
Thank you, Aline. We are looking forward working with you in the future. Thank you. Bye-bye.